Today we're starting up a section that changes our focus a little bit away from triangles. It's still triangle involved, but it's not all triangles. It works with other ways that you can have proportionality. So that's not something that's specific to similarity. First couple are triangles, the first couple of theorems. The triangle proportionality theorem and its converse are going to be the first things we talk about today, and they're fairly easy, and they're actually going to look fairly similar to problems that we've done before. The difference is how we set up the proportion. The triangle proportionality theorem states that if we have a segment going through the middle of a triangle that is parallel to one of its sides, so in other words, in this picture, that means if BC is parallel to DE, then those lengths that get cut in a manner that is proportional. So in other words, if I want to solve for things regarding a picture that looks like this, I don't necessarily have to do full side length of triangle over full side length of triangle equals another full length over the smaller triangle's full length. Instead, I can set up a proportion that looks like AB over BD equal to AC over CE. Now my first fraction is set up of lengths that came from the same side of the triangle. The second one, same idea, where AB and AC were both on top because they came from the same general area. They came from the same side of the parallels specifically. And same with the denominators. They came from the same sides of the parallels. So that's the triangle proportionality theorem. Or triangle prop theorem if you'd like to shorten it. Not that it's going to show up in proofs, but we're going to justify answers using it. Then we also have its converse. What does a converse do to a theorem?
It's kind of like reflective property. Inverses it, sort of.
Inverse is actually another word for it. It flips it. Reverse is typically the word I use. I knew exactly what you meant, Savannah. You're right in how you were describing it. And I know a couple of other people were describing it as well. I didn't quite hear everyone. But yeah, it flips the order. This one states that if that proportion is true, AB over BD, if that is equal to AC over CE, then I'm able to say that BC is parallel to DE. So we're going to start by using these two theorems. The regular theorem starts with parallel, tells us proportional. The converse starts with creating a proportion to tell us that something is parallel. So some of these are going to start off real basic, like these ones here, that say find the lengths of, this one's RQ, this one's YZ, rounding to the nearest hundredth if necessary. So I look at my picture. Do you notice there is not a single variable in that picture? Which means we can add variables in places that we need if necessary. I'm looking for the length of RQ, which has no labeling whatsoever. I need a label on it. I'm going to put some sort of a variable. X, sweet. Okay, and according to that theorem then, I can set up the proportion X over, now in all technicality, it doesn't matter which length you start with when you're using these theorems. It's just a matter of being consistent on what goes elsewhere once you've started with the side. If I start with X, underneath it goes the length that came from the same side of the triangle. In this case, that would be
9x.
Just the 9. So X over 9 equals. Now, if X was on top of the other fraction has to go the 4, which is by it. And it would be 4 over 6. How do we solve something like this? Cross multiply. Do you trust my cross multiplication skills?
On this one, yes.
On this one, yes. On others, maybe not so much. Okay, fair enough. X is 6.
36. It is.
It's 6. Because I get 6 times x, which is 6x. 9 times 4 is 36. Divide by 6, and x is 6. So, x is equal to 6. Now, did it say solve for x?
No.
No, it said solve for the length of RQ. So, I have to change it back into RQ. Do I put the bar above it?
Yeah.
If I put the bar above it, I'm calling RQ's name. Is RQ's name equal to 6?
No.
No. RQ's length is. Do not put the bar above it. By putting the bar above it, you're saying something's name is that number. That would be like calling you guys by your age and expecting you to answer, hey, 16. If you're 16 years old and someone says, hey, 16, do you think I'm talking to you?
Most likely.
Oh, if I say 16-year-old, but no. Generally, if I say, hey, 16, everyone's like, what are you talking about? Why are you calling a number? So, do not put the bar above it. Bar above it is the name. But we change it back to the proper notation, we move on. Next one says find yz. Yz also doesn't have a labeling on it, so I'm going to use a variable. I like x. Now let's say I choose to start with x on this one. What has to go underneath it? 36. Comes from the same side. Equal to? Top of the other fraction? 35 over 44. Now, in all technicality, I heard someone just very, very slightly whisper that underneath the x should have gone the 35. Now, here's the thing. If I had put x over 35, and then in the other fraction had done 36 over 44, x gets multiplied by 44. On this one, doesn't x get multiplied by 44? 35 gets multiplied by 36. Doesn't 35 get multiplied by 36? It's an equivalent proportion. If you did it that way, you'd still get the right thing. You're technically not following the theorem perfectly, but when it comes right down to it, there's a lot of equivalent proportions, and if you had done it that way, you'd be fine. Do you trust my cross multiplication skills on this one? Sure. X is equal to 28 point. Now it goes 6, 3, 6, 3, 6, 3, 6, 3, 6, 3, 6, 3. If I'm rounding to the nearest hundredth, that would be 6, 3 or 4? 4. And then don't forget to change it back into YZ, which is what it actually asked for in the first place. So far, nothing too scary? Okay, let's flip the page. Very scary so far? Ooh, that's concerning. Okay, on the next page, I've got this triangle which has some parallel lines going through it. Now those parallel lines are what makes it that I can use the triangle proportionality theorem. Now I can do things that we've previously done where we find full side lengths if we want, but it's easier not to if I'm not given full side lengths. That's why we set things up the way we do. I want to find the length of RQ. But now I've got variables involved, so I'm going to use the variables they gave us and then plug things back in later. I could start with any of these lengths. I just got to make a choice. Which one do you want to start with?
15.
Sure. 15 would go over the top of what? 10 by the theorem, technically. If you put it over x plus 1, it would have been fine. What goes on the top of the next fraction if we do 15 over 10, though? X plus 1, because the 15 comes from the same area as the x plus 1, the 10 from the x minus 1. So x minus 1 goes here. I cross multiply. When I cross multiply, anything with a plus or a minus needs what? Parentheses indeed. 15 gets multiplied by an x minus 1. 10 gets multiplied by an x plus 1. For some reason, this step messed with some people on quizzes, so let's just address that. when I'm doing the, what's this thing called?
Distribute.
When I'm doing distribution, what operation am I doing? Multiplication. I'm not adding. Far too many people added. It wasn't actually a whole lot of people, but some people did, and it made me sad. 15 times x.
15x.
15x. 15 times negative 1
Negative 15.
equal to 10 times x.
10x.
10 times 1.
10.
Okay, so I subtract my 10x from both sides. I add my 15 to both sides. I'm going to do them both in the same step. Save myself a step. It's not a proof. I can skip steps if I'd like. 15 minus 10. 5. Don't forget the x. Equals 10 plus 15. 25x is 5. Is x what it asked for?
No.
No, so we're not done. I want RQ. RQ starts here, ends here. What am I plugging into? X plus 1, x minus 1? Both.
Plug in both.
Oh. This part, 5 plus 1 is 6. This part, 5 minus 1 is 4. RQ is 10 because I add them together. So that's our triangle proportionality theorem at work. Now the next problem starts using its converse. How do I know it's using its converse? We're trying to determine if things are parallel. In this section, that's the only option we have. In triangle DFE, DH is 24. HE is 36. And GG is 2/3 GF. That is all together. That is not a separate equation. That's not a typo. That is together. DG is 2/3 GF. Determine if GH is parallel to FE and justify your reasoning. Now, the only justification we can possibly have for if it is or if it is not is the converse of the triangle proportionality theorem. So, that's what we're going to be using, and that theorem states that if we have the proportionality, then it works. So, I'm going to try to write a proportion, and I'm going to see if that proportion works. I'm going to start with 24. 24 is going to go over to the top of, 36. Now, the other half of the proportion becomes a little more challenging to work with. So, there's a couple of options on how to do it. One option is working with the side lengths as names. And while this works beautifully, it tends to trip people up a little bit because we don't like working with things like GF in an equation. So instead, I'm going to replace it with a variable, which tends to be a little bit easier. Now, the variable should go on something that I don't know what it is. Now, I don't know this and I don't know this, but it's going to be easier to put it on the GF because the GF I know nothing about. I'm going to use the variable x. In other words, I'm saying I'm replacing GF and setting it equal to x, which means this 2/3 GF can be written as
2/3 x.
2/3 x. Now, creating that second half of my proportion. Does the x or the 2/3 x go on top? 2/3 x goes on top because it needs to be in the same general location as the 24. Over x. Now, to see if a proportion works, traditionally, you simplify the fractions. Or there's another option. I can cross multiply, but not for the sake of solving. I can't solve an equation that looks like this, but I can see if it gives me a result that is always true or not. So here's what that looks like. I go and I cross multiply. 24 times x is real easy. 24x. 36 times 2/3 x. Now, a little more complicated, so I'm going to write it out, but how do I do 36 times 2/3 the easiest way possible? That's even harder, turning it into a decimal than what I mean.
24.
It's 24, how'd you get it?
Divided it by 3 and then I just added 12 to it.
But essentially you typed it into your calculator. 36 times 2/3, ta-da, 24. Or yes, you can divide by 3 and then multiply by 2. 24x equals 24x. Because don't forget to put the x back on. Now I cannot solve an equation looks like this. Again, I'm going to emphasize that. You cannot solve this. This is infinitely many solutions. I don't care about solving it. I'm just trying to see if it's true. In other words, if those are the same. Is 24x the same as 24x?
Probably.
Yep. And if those are the same, then GH is indeed parallel to FE by the converse of the triangle proportionality theorem. If they were different, I would say they are not parallel. Again, by the converse of the triangle proportionality theorem. Try out E on your own. Careful on this one, they give you HF, not PF, but you can find PF. Okay, I'm not gonna go through the entire thing yet. I know some people need a little bit more time, but I'm seeing some people make a common mistake, so I want to address that before we get too far. In order to do my theorem, I need the parts of the triangle. I was given HP is 24, HF is 150. How do I get this part? Subtract. If the full thing's 150 and part's 24, we subtract to get there. Segment addition postulate working backwards. That part's 126. Do not put the 150 into your fractions. It's not going to help you. Okay, continue. Okay, I'm going to start going through it. Not quite everyone's done, but I want to be cognizant of time. Okay, I was given that QG was 11 halves HQ. Where am I putting my variable? Just the plain variable. HQ, which means this is 11 halves X. If I chose to start my fractions with X, what would go underneath it?
11 half X.
Should be the 11 halves X. If you did the 24, it would work, but technically you're not following the theorem. So you should have these two on the same side of your fraction. Okay, equal to, is it 24 over 126 or 126 over 24?
24 over 126.
24 over 126. Cross multiply, x times 126 is 126x. That one's real easy. 24 times 11 halves x. 24 times 11 halves is what?
132x.
Do not forget to put the x back on it. Are those the same?
No.
No. So, not parallel because the sides are not or the parts are not proportional. Okay, we're going to do just one of the two problems that's on the bottom, and then we're going to move on. One of the two problems, these two problems on the bottom are following the same idea. The only difference is I didn't give you the picture. I tell you, there's a triangle ABC. So I recommend you draw out ABC. E is between A and B. E. D is between A and C. D. Determine if CB is parallel to DE. Now in my picture they do not look parallel, but does that tell me anything?
No.
No, I drew the picture. If they looked parallel, I wouldn't know any better than if they didn't look parallel. I just put points between and connected them. Sometimes you're going to see these same types of problems as above, though, where they give you, okay, that's 12, that's 14, this is 18. All the way across was 39. I should have drawn this slightly differently. I ran out of room for myself. I'm not doing this problem anyway. So all the way across was 39. What's that make this part?
Is that a 16, by the way?
21.
That's an 18, that's a 39.
21.
It's 21 right there. Sometimes they're going to ask for parallel, but they're not going to give you anything that involves a variable. If you get a problem like this, you're still going to do this stuff. You're just doing it all with numbers. I start my proportion, I do something like 12 over 14 equals 18 over 21, and I see if that's true. I can either simplify the fractions or cross multiply. 12 times 21, if I chose to cross multiply, is 252. 14 times 18 is 252. Is CB parallel to DE?
Yeah.
Yeah, those are the same. Converse triangle proportionality theorem. So sometimes they might just give you just numbers. You do the same thing. Okay, triangle proportionality theorem and its converse. We okay with that?
Yeah.
Okay, we do have a few more theorems we're talking about today. Next one's the triangle angle bisector theorem. Triangle, angle symbol, bisect, theorem. This one states that if there is a ray that bisects one of the angles of a triangle, then it divides the opposite side of the triangle that segment or that ray intersected into proportional parts that are proportional to the other lengths of the triangle. Now that's a bit of a mouthful, even in my reworded version versus their version. Essentially, if AD, that's a ray, so I've got the ray symbol, bisects. Now it bisects an angle. Specifically in this case, it bisected angle A. Or more accurately, no, we're not going to put A. We're going to put BAC. And then I'm going to write it incorrectly for no reason. My bad. It was clearly never there. There we go. AD bisects angle BAC. What does it mean to bisect?
Cut in half.
Cut in half. More specifically, it actually means to cut into two congruent parts. But yes, cut in half. So, what got bisected here?
Triangle ABC.
Not triangle ABC. Angle BAC. When you cut an angle in half, what do you make?
Two triangles. Two congruent.
Two smaller angles. You cut an angle in half, you make two angles. You cut a segment in half, you make two segments. So I have two congruent angles that got formed here. This one here and this one here. That is the requirement. That is what we are going to see in the picture. If you do not see those congruent marks on the angles, you cannot use this theorem. You must see those congruent angles. If you have those angles congruent, then these two segments that got formed when the ray came through the middle are proportional to the side lengths that are still here. So BD, oops, I forgot the word then. BD over DC is equal to AB over AC. The first fraction is made up of these two segments. The second fraction is the side lengths, keeping in mind that BD being on top meant the side next to it was on top. DC on bottom, the side next to it went on bottom. You have that relationship of where they're located in the proportion and in the triangle. So, we're going to find the value of the variables, routing our answers to the nearest hundredths if necessary. Okay, so do you see the congruent angles in this picture? Right there.
Yes. Yeah.
They're a little tiny, but they're there. So that's what tells me I can use this theorem. And that theorem says divide these two lengths. Do I know both those lengths in this picture? Are they labeled?
Yeah.
They are? What are they labeled with?
X.
X and?
Probably
15
15. Wait, no.
minus X. This length is not labeled, but I know the full length. If I know the full length and I know the part of the length that I don't know is those two subtracted. Now, it's a little bit harder to think of if this was X, but if I said this was 10, would you easily come up with that being 5?
Yeah.
Yeah. So, this is X. You follow the same process. RQ, or QR, I guess is what my hand decided to write, was 15 minus X, because it's the full segment minus the part of the segment that I didn't want. So that's what goes there. 15 minus x. That's what goes in this side of the fraction. 15 minus x. Is 15 minus x the same as x minus 15?
No.
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 Adding can go in either order. Subtracting cannot. Subtracting must be big minus little for this case. Okay, equal to. Now I put x on top, which means for full side lengths, the full side length that goes on top is 13 over 7. Guess how we solve?
Cross multiply.
Cross multiply. 7 times x is?
Probably
7x. 13 times 15 minus x needs parentheses. 13 times 15 is 195.
Sounds right.
13 times negative x is?
Negative 7x. Wait, no. What? Negative, wait, huh?
Negative 13x. Be careful. Far too often what I see people do is they go too quickly. They don't put the x right there. They put the x right there because x generally comes first in things. But does the 195 have the x on it?
No.
No, the 13 does. Be careful. I know you know better, but I also know that some of y'all like to rush and get things done and don't pay attention to details. Okay, I want to solve this. What am I doing?
We're gonna plus 13 to the other side.
Add 13x to the other side. I get 20x equals 195. Divide by 20. It is going to be a decimal. 9.75. Trial B.
Do we have a worksheet or a book assignment today?
Both, clearly.
I hate my life.
It's a worksheet. It's a worksheet. The answer is on the back board if you just turn around.
Yeah.
Oh.
Nobody's saying I should do the fiction or read.
So you've been going most of this class about a
No,
page?
it's just this page. Every other page.
So you had it flipped around. I'm going to staple it back together, please. There we go. Let's say, like, you would have lost more than one page. They're back to back. That'd be perfect. Wonderful.
Wait, we're gonna drop. These are optional.
You set up like this? Yeah. Wait, no. So it'd be x is no.
Proportion. It will work.
Oh, well,
It
what-
will work.
Like if I were to actually go right and do this one, I would.
Yes, this one over this one, that one over that one.
Yeah, repeat every 2 hours as
Are we doing homework now?
I said trial B.
What'd you get?
that you're supposed to.
Hey, why aren't you trying out B?
You got what? You got 28.
Wait, why did I do it?
I think you put the things on the wrong side.
Okay, we're going to start going through it because far too many people are not doing it, and then we're going to address that fact in a minute. Okay, if I want to set this up properly, if I start with the 14, what does it go over the top of?
14 goes over the top of x.
Equal to?
Which is equal.
24.
Thank you.
Yeah.
To 24 over 48.
Correct.
We cross multiply, and we'll get 28.
Yeah. Go team. Go math. Math moment.
Okay, we got one more theorem we're talking about today. The last theorem we're talking about today is the three parallel lines theorem.
Can that be abbreviated with just the 3?
It's gonna be 3 parallel symbol. And then lines.
This one states that if you have 3 parallel lines, I know, shocking.
Did not see that one coming.
I would.
Good job, Chase.
Thanks.
So I got those 3 lines, they are parallel. And they are being cut by 2 transversals. Now when I do that, I'm going to have a lot of intersection points involved that I need to name. That one's A, that one's B, that one's C, that one's D, that one's E, that one's F. Now those 3 lines need to be parallel. The transversals do not need to be. If I have that, then the chunks, the segments created by the transversals going through the parallel lines, specifically the chunks that are on the transversal, not the ones on the parallel lines, those are proportional. AB over BC equals DE over EF. So if you see those 3 parallel lines, you can make a proportion with this one as well. Problem like this one. I'm going to start with the 2x minus 10. I see the 3 parallel lines, so I know I can make that proportion. 2x minus 10 would go over the top of what?
10. 4. 5. 10. 4.
10. Equal to. The other side of the fraction would look like?
4 over 5.
4 over 5. And we can solve for x by cross multiplying. By now you know that I can cross multiply, I hope. X would be 9.
Yeah.
I'm not going to spend the time cross multiplying that one because of the fact that that's been something we've been doing all chapter, and I want to focus more on giving you work time today rather than practicing something we've been doing for 2 weeks. Okay, this is going to be our last problem that we set up today. Then we're going to have a quick conversation before I give you your homework. So, final problem. Do you see the 3 parallel lines?
No. Yeah. Yeah.
So I'm doing this theorem. I'm going to choose to start with the x minus 1. That x minus 1 needs to go over this length.
It'd be.
How do I find it?
We don't know x, so it'd be 16 minus x minus 1.
It would be, but you have to be careful. If you write it like this, you're going to miss something. It is not 15 minus x.
15 minus x.
It's not 15 minus x. In this setup, what I actually just subtracted is I said, I'm going to take this 16 and I'm going to subtract x. But that minus 1 was already there. I'm supposed to subtract the entirety of x minus 1, which means I need parentheses. When you're subtracting a binomial, that binomial needs to go in parentheses. Because now this subtraction here is not just on the x, it's on the x and on the -1, and it gets distributed through. 16 minus x minus a negative,
That'd be positive.
be adding 1. That length is 17 minus x. It's not 15 minus x. You have to be careful of that. When you subtract a binomial, it goes in parentheses. When you multiply by a binomial, it goes in parentheses. When you divide by a binomial, it goes in parentheses. The only time it doesn't go in parentheses is adding. So, 17 minus x goes here. Equal to 3 over 5. I don't know this one off the top of my head. I haven't done this problem yet. So I'm just going to quickly go through it. Y'all know how to cross multiply. X is 7.